Okay, we're all set.
Okay, thank you, Ken. Well, the title of my considerations today is more or less the same as it was last year and 2 years ago, maybe with the one or other new aspect. It's the mental influence on the physical that should happen without violation of conservation laws. I think that's an issue we've been discussing uh, all the time, actually. The assumption that I make is that mind can make choices during the temporal evolution of biological systems. In other words, it can intervene and cause deviations from the course of action that otherwise would have been taken by the system. And the concept that can do this is selected reduction of entangled quantum mechanical wave functions. And the core idea is the following. You can think of a liquid like in a membrane of a neuron, where you have ions and water molecules. And then if any two such particles interact, which in a liquid essentially means they're tossing on each other, then immediately after that interaction, you get a superposition of possibilities of how the two particles move apart again. That's what I've symbolized here in this drawing, that there are many possibilities, like, for instance, the heavier particle, the blue one, goes in this direction to the left, and then, of course, the red one would have to go in the opposite direction. All this is seen, of course, in the frame of center or of zero momentum, so that in the center of gravity, actually, of the two. Okay, and then in the normal course of interactions, if you do not consider decoherence, this would go on. Each of these particles would hit other particles, and then again you have a splitting of possibilities, and all this would be a huge wave function. But practically, you can say already after a very short time until each of these, or actually when each of these possibilities hits other particles, then the coherence has set in, and then essentially one of these possibilities will be actual. And then, of course, with the next tosses, again, you have superpositions, etc. But which of these possibilities is normally chosen is completely accidental and follows in accord with the quantum mechanical rules. There are, of course, different weights for all of these possibilities. This depends on the velocity of the particles, on their substructure, etc., so that not each of these possibilities has equal weights. But with these weights, normally these things happen. So, for instance, they could move apart like this. And my idea now is that mind can select one of these possibilities, depending on what it wants to achieve. It's important to note, of course, that each of these possibilities conserves angular momentum and energy and ordinary momentum. All the physical quantities that have to be conserved in an evolution are conserved by each of these possibilities. That's important to know. So if mind picks any of these, then the conservation laws of physics are automatically fulfilled. If you want to write this down formally, before a collision, you have, say, these two momenta, then immediately after a collision, you have a superposition of possibilities. And then after a selection, here in the drawing, it's momentum K2 in the two directions. You would have this state where the only K2 is available. And this could be an action of mind. Now, if mind does this repeatedly, in a liquid, then of course it can achieve directed diffusion. Imagine here you have various ions in water here, and sorry, I think something's wrong here. Should I? No, can you see my cursor? That's the important thing.
Yes.
Yeah, okay, good. So here, initially, the ions are distributed quite homogeneously. And if mind interacts at the collisions and chooses directions it prefers, then, for instance, red might not be allowed to scatter to the left side, and blue might not be allowed to scatter to the right side. And after some time, of course, you have a collection of red particles on one side and blue particles on the other. And such a phenomenon could happen, for instance, in the axon hillock of a neuron. And that could lead to an accumulation of charges of the right polarity, which could overcome then the normal resting potential that is usually there between the inside and the outside of the axon. And that could be sufficient to start a neuronal pulse, and that will, of course, travel down to the synapses and then transmit signals to other cells. I've calculated this in detail, as you know, in this paper that I uploaded to arXiv. So this was my idea of how a neuronal pulse could be initiated. Well, and that was the state of affairs, but of course there are quite a number of open questions. And I've listed 4 in my abstract, and I want to go through those 4 open questions. And one of them is, does mind intervene at the level of pairs of entangled particles or at multi-particle entangled molecular groups, or at an even larger context? When I ask this question, this is essentially already a speculation about the mechanics of mind, right? Because how could we possibly know at which point and at which interactions mind wants to interact? But I want to do some speculations here. And a reasonable assumption that one can make is that mental interventions happen at a rate that's similar to quantum mechanical coherence times, or actually a little bit faster. Because if mental intervention were slower, then it couldn't actually intervene at all the possibilities it might want to intervene. Of course, it's conceivable, but let's assume it does intervene with a frequency that's similar to quantum mechanical coherence times. Then for the ions in water that we just discussed, and we're looking at 2 particle states, then their coherence time is typically only about 10 to the 12 seconds or even less. So that's essentially the time between collisions. And mind really would have to interact at such a frequency. Then if there are many particle states, say, if mind sort of traces the evolution, the quantum mechanical evolution of a larger volume in water with with ions, which is conceivable because as soon as you take a larger system, you don't have decoherence. If you take, say, 1,000,000 particles and say, I want to treat them now quantum mechanically, you can do that. And then you have coherence times over many collisions between the particles, actually, until the outermost particles start interacting with an external environment. But as long as that is negligible, you can think even of 1,000,000 and more particles as being one coherent volume. because decoherence is always an admission. I can't describe more than, say, this volume. So that leads to some certain coherence. But if you increase that volume that you want to describe quantum mechanically, coherence times can be relatively long. And they certainly then have to stop when the volume you're considering interacts, say, with the remote environment by means of thermal radiation. And you can hardly shield this. And with Penrose, of course, you'd have to argue also that as soon as gravitational interactions start playing a role, and of course, this also would lead to decoherence. But you can achieve, in such a consideration, larger coherence times. And then you could say mind need not interact at such a high rate. It lets a certain volume evolve. And then after some time, it says, okay, out of all those trillions of possibilities that are now in superposition, I pick one or a group of possibilities and let the system evolve from then on further. And for very large systems, this can be maybe microseconds even. And with computers, of course, we're trying to reach even longer times with quantum computers of coherence of quantum systems. And in fact, there might be a trade-off of the following kind. If mind intervenes at the two-particle level, say in the liquid, then it needs many interventions. And at each of these interventions, it needs to pick a possibility, maybe with only a moderately low probability. However, if mind considers a larger volume and lets it evolve, and then wants to get things its way, then it may have to choose out of those trillions of possibilities, then one possibility with an extremely low probability. Of course, it gains that it doesn't have to interfere so frequently, but can do so maybe only at the microsecond level or even slower. But what I also want to say is that I don't think that we necessarily have to confine mind to be interacting in a neuronal system. It could also interact peripherally, maybe even at the activation of muscles directly. Because if mind has, say, a holistic approach on an organism, it may act in a very goal-oriented way and do things in the brain and muscle fibers in the peripheral nervous system, all in, say, in a coordinated way of wave function reductions at various locations and achieve, say, its goal in this way. So you see, as soon as you start thinking of how mind could possibly act, you really have to come up with all kinds of speculations. Okay, the second open point that I listed in my abstract is that mind needs an overview of what is possible. Because how else would it know which decisions it can take and influence the biological system? Well, on the one hand, you have the information which is consciously and subconsciously available in the organism. And then you might argue, okay, this information is processed in a normal physical way. Mind hardly needs to interfere there. It just waits for the result of such a process. And then maybe that process itself gives only a few possibilities. And then mind can interfere at say, at the end of such a normal computational process in the organism. But then there's this statement of Moravec that always stays in my mind, and this is his statement that mind is the information a system has about itself without taking a measurement. And I'm still wondering what he meant by this. It's not fully clear to me. Does he mean that mind has sort of a grip on an organism similar to the way the laws of physics have a grip on every proton, every electron? Protons and electrons just know what to do according to the laws of physics. And maybe mind has this grip on the biological system in the very same way, that it just really knows everything, like a real super Maxwell demon, um, knows everything and can really say, lean back and decide I do this or I do that. But that will, of course, imply that subconscious awareness of additional possibilities of action are there. And by subconscious, I mean not subconscious at the level of the neuronal system, but really at the very molecular level. But I haven't made any progress on this, so I'm essentially just listing this open question here. Now, let me get to my third point. And that is a little worrisome problem. It's the following. The active mental selection of part of a wave function amounts to a form of wave function reduction not covered by current quantum theory. That's something that should be stated clearly. If two particles collide and they move apart in a superposition, and that superposition then collapses to one of the possibilities according to the weights of quantum theory, then that's normal decoherence, and we don't worry about it. But if mind selects a specific possibility, and you follow that through, then you find that you reach the possibility of influencing the environment without physical interaction. And I want to demonstrate that now to you. I've done a little simulation to really see how this happens. And for this purpose, I've modeled a biological system. That's these 4 spins here. So these are spin 1/2 particles. And then the environment by 10 spins, okay? And of course, in the real world, each spin interacts with every other spin. And there's a probability when they interact for a mutual spin flip or for a little, say, opposite tilting of the two of them. And if this interactions between spins of one system, say here of the biological system, that will of course be a strong internal interaction. So this probability for spin flip, for mutual spin flip, has a rather large value of 10 to the -3 in one time step. And the same for all the spins in the environment. And then there's only a weak interaction between the two domains. Say the spins here interact with the spins in the environment only weakly, say with a mutual spin flip probability of 10 to the -6. So here we have altogether 14 spins treated as one quantum mechanical system. Of course, you have 2 to the 14 base states, which is more than 16,000 basis states. And I've written them down here in the usual way that you would write down a state in a quantum computer with 14 spins. Like here, you have an amplitude for all 14 spins being in the down state. Then the next one is a certain amplitude for the first 13 spins being in down state and the last spin in the up state. And the next one is a certain amplitude for 12, and then the last one in the down state and the 13th spin in the up state. then this one here is the amplitude for the first 12 spins in the down state and the 13th and 14th spin in the up state, and so on, etc., until you have gone through all the possibilities, and then you have those 16,000 basis states, and each of them has a certain amplitude, and that's the quantum mechanical state of the system. And then with this rule of interaction, you can let them interact, and the whole system evolves. And the rule for evolution, if I would write it down for all of them, it would look rather ugly. So I've just picked 2 spins, and then it's easy to explain what happens. Say you have a 2-spin system, then the state is given by this, a certain amplitude for both being down, an amplitude for the first one being down and the second one being up, another amplitude for the first one being up and the second one being down, and the final amplitude for both of them being up. So these are the possibilities, and this is the spin state of these 2, or the total quantum mechanical state of these 2 spins. And now the rule for interaction is such that, of course, we have to conserve angular momentum. It's not possible that the 2 interact and the total angular momentum changes. It's not possible. So what possibility does exist? That only these can change, so that there's a mutual spin flip, a certain probability for it, only if one spin is up and the other spin is down. So only these 2 amplitudes can be affected by an interaction, and this one cannot be affected. And now I can define this alpha and beta quantities as 1 minus p square root, and beta is the square root of p. And for p, you have to take p internal in our case here, if it's an internal interaction, for p between, if it's an interaction between a spin, say, of the biological system and the environment. And of course, the interaction within the environment also follows the internal field. Okay, but let's return to our 2 spins here. The rule for interaction now is the following: 0, 0 goes to 0, 0, 0, 1 goes to alpha 0, 1 plus I beta 1, 0. And the same must be true for the other possibility. 1, 0 goes to alpha 1, 0 plus I beta 0, 1. And 1, 1, of course, goes to 1. So after one time step, this was the initial state. After one time step, these 2 spins now are in this state. So what has changed? The amplitudes here have changed. And this, of course, can now be applied to this system. But one should note, if I apply the same rule to this system, if any 2 spins interact, it means that actually half of all the amplitudes are changed, only if any 2 spins interact. This is because the whole system is totally entangled. Now, a rule for pairwise wave function reduction. That's what mind is supposed to do in the end. How shall that rule look like? Well, I said in the beginning, the idea is that after an interaction of 2 particles, mind chooses one of the possibilities according to what it wants to achieve. In our case, in order to conserve angular momentum, it's only possible that it either reduces the 1, 0 state to 0 or the 0, 1 state to 0. So immediately after an interaction, say you have this state, and then mind intervenes and says, I cut out this possibility. Or it says, I cut out this possibility. Of course, this means that immediately after the reduction, you have to renormalize the whole system. So you get different values for A0, or this amplitude here, or this amplitude here. For a multi-spin state, as we're considering here, this implies that if mind makes such a selection with only two spins when they interact, that 1/4 of all the contributing basis states disappears immediately. So out of those 16,000 basis states, if any two spins interact and you have a reduction by mind, then 4,000 of these possibilities immediately disappear. Okay, so much now for an explanation, and I've let the system evolve for some time. First, I let it evolve for I think 400 time steps. It was a normal quantum mechanical interaction, no interference by mind. And what I've plotted here, the y-axis is the angular momentum of the biological system in red. Okay, so that's the total angular momentum, which is, take, say, for the biological system, you take what's the expectation value of the total angular momentum of those four spins. And for the environment, you take the expectation value of all the green spins. That's what's plotted here as angular momentum. And you see they start off, the initial state was a random state, where I made sure, of course, that the total angular momentum of the system initially is zero, but I didn't look whether individually this would be a zero angular momentum state. That was not necessary. That is not necessary. You can say, I start with certain angular momentum here, total angular momentum. Then, of course, the environment should have the opposite total angular momentum. And that's what you can see here. They don't start from zero. But then they evolve according to the rules, and it's a normal quantum mechanical evolution. You see they actually evolve a little bit apart. So that's like somehow the whole thing starts to rotate. The internal system, let's say the biological system in one direction and the environment in the other direction. And then I start, or I let mind interfere. Okay. And the rule for the mental intervention is this, that after every 50 time steps, mind just makes a wave function reduction at two spins, but only at spins in the biological system. Okay, so you could say, for instance, I take these two spins here and make a reduction according to the rules that I outlined. And then it, of course, it has implications for the whole state. Then the normal quantum mechanical evolution for another 50 time steps, but no more interaction between the environment and the system. That was important because I wanted to find out if I only have interactions here in the biological system, or reductions, wave function reductions in the biological system here, and no more interaction with the environment, does the environment get affected nevertheless? Okay. So then, of course, after this reduction, what you have is the angular momenta cannot change anymore because there's no more interaction between the environment and the biological system. So the evolution just shows you angular momentum stays constant for the environment and constant for the biological system. Then after 50 time steps, another mental intervention happens in the biological system here. Some other two spins get reduced to a certain state. And you see it accidentally puts the momenta in this way that the biological system jumps up in angular momentum and the environment jumps down. And this is already, of course, relatively surprising, right? Because there was no more interaction, or there is no more interaction between the two. There's only internal interaction within the environment and internal interaction within the biological system. And then I let this whole system evolve further. And here you have now the full time scale. This goes only until 500 time steps, so that's about here, right? And then it continues in this manner. 50 time steps, normal quantum mechanical evolution, but no more interaction between biological system and environment. Then a wave function reduction in the biological system. Then again, 50 time steps, normal evolution, etc., etc. And the goal is, and this is where mental steering comes in, that mind chooses its wave function reduction such that a certain goal is reached. And the goal here is that the angular momentum of the biological system should become maximum, right? And you see that this is actually what slowly happens. The angular momentum of the biological system increases. Here, this sort of they get oriented more and more, say, upwards, and there must be a corresponding orientation of the green spins more or less downwards, right? But of course, they must compensate each other because the total system has zero angular momentum, and you can see that this is actually the case. Well, this is worrisome, I must say, because how should this happen, right? You have wave function reduction in the mind, in the biological system. You have no more interaction with the larger environment, and yet there is an effect on the larger environment. That's what you get. And now I want to show you a little bit how this looks like, simply because it produces nice pictures. Just a moment. Okay, so what you see here is now this actual simulation. Each of these little dots is one amplitude. You can read here the state here and the amplitude it has. And of course, it's complex, so it also has a phase. For instance, if we look at one here, this one here is this particular state. I should say the last 4 digits here, they are the spins of the biological system, and the 10 first spins are the spins of the environment. So you see the bright ones indicate a large amplitude, and the less bright ones here indicate a relatively small amplitude. And you can let it evolve. Say it starts like this. And now there's no more interaction between the two. Now you've noticed a reduction of wave function. I go back maybe. So this is before reduction, and then the next time step brings a reduction. You see immediately 25% of all the amplitudes disappear, but of course they are repopulated because there's, again, interaction within each subsystem, within the environment, and of course also within the biological system, but not between the two of them. Well, and so it goes on, and ultimately you should see that one system gains a lot of angular momentum in one direction and the other in the other direction, because then some of the amplitudes get very bright and the others get very dark. And you can see this already now. You have relatively few relatively bright spots, which means that many of the spins of the biological system must point upwards. That's what it means. And if we look at one here, for instance, you see the last 4 digits are all up. And that's a very bright spot. So that's a very large amplitude that the biological system has all 4 spins pointing upwards. Okay, that's just what I wanted to show you here.
Johann, there
Yes.
appears to be like diagonal streaks. Is that just a
Yes.
Artifact?
Yeah, that's a good point. This it follows from the requirement that the total angular momentum must be 0. If I had not put this requirement, you'd have gray and white dots all over. But the interesting thing is they would sort of evolve separately, right? And I wanted to only show, say, the situation for the whole system having zero angular momentum. So that the result that if one starts turning in one direction, the other starts turning in the other direction without there being any interaction becomes more clear. But you're right. If I plotted all, if I had chosen another random system, you'd have white and gray dots all over.
Okay.
And maybe it should also be mentioned that it's not only the angular momentum that is reflected in the environment. I mean, the angular momentum of the biological system that ultimately gets reflected in the environment. It's also more detailed patterns, say, of the force spins of the biological system can be found as a pattern in the environment. And I consider that also very, very interesting. It's like certain patterns of mind are somehow spread out all over the environment with which the biological system interacts. Of course, it's extremely difficult to identify them. Okay, and then there was a fourth open question that I had, but I didn't get any further in my answers here. And this is a test of mental influence. And one should note that if mind's wave function reductions happen with the normal weights of quantum mechanics, there would be no influence on the organism, or it would be indistinguishable from normal physical law. This is simply because if you think of collisions between ions and water molecules, etc., without any influence of mind, then you immediately have decoherence anyway. And then one of the quantum mechanical possibilities becomes actual, according to the weight as determined by quantum theory, but one of them is actual, and then the system continues. And if mind happens to choose the possibilities with exactly the same weights, then its action would be indistinguishable from normal quantum mechanical. Mind becomes only, and I think this is what Dejan also said, mind becomes only detectable, or the traces of mind only, if there are deviations from normal statistics. That is, there must be very unlikely possibilities of the physical course of events must happen. Then you have a chance. I think this is, in my opinion, this is the only signature that mind can have. If something extremely improbable happens, then you could say, looks as if this was an influence of mind, right? So, of course, in practical technical terms, it means a decrease of entropy. But if you admit that this is the only trace that mind can leave in nature, things that are physically possible but extremely improbable, if they do happen, then you could say they're a trace of mind. Then should we see any rare event as ultimately being caused by mind? I think that's a difficult question. Personally, I tend to say yes, because it seems to me there's no other way for testing mind than by looking for extremely low entropy things. Of course, you can test this only with repeatable settings. And if you would say then, of course, the evolution of life on Earth is an extremely improbable thing. But my question would then be, how would you test that, right? If you have an argument why it would in principle be testable, then okay, then you might come to the conclusion that also the evolution of life is ultimately governed by some form of mind. But anyway, the open question is, should we consider any event that is extremely rare? And by extremely rare, I mean really, I don't know, probability of 10 to the minus 10 or something like that. should we say this is a trace of mind? Yes or no? I don't know. And well, with this, I want to stop now.
Well, thank you. Well,